Welcome. In this section, we're going to go over some different considerations for laser systems and give an introduction to some parameters in laser systems. While lasers are not the main focus of this course, they are a common component that is used in optical imaging, and having an understanding of some of the basic terminology and ideas will help you in your future optical design processes. So lasers, or light amplification by stimulated emission of radiation, are devices that produce highly coherent directional beams of monochromatic light. The basic structure of any laser is based on a cavity that confines light and an active media within that cavity that the light interacts with and uses stimulated emission, which creates the coherent pairs of photons. The light's contained between a couple of reflectors, and one of the reflectors will be partially transmissive, allowing the light to escape, creating a beam in that direction. So there's a vast array of laser systems, and many of them are used in optical systems for imaging, as well as many other applications. So the goal of this section is to introduce some of the key parameters and terminology around lasers, so that we have a common framework to discuss optical systems involving lasers. So first off, wavelength. Lasers are monochromatic, so they have a particular wavelength they emit light at. In reality, it's a spectrum with a peak wavelength, and we specify the laser's wavelength as the peak wavelength in the spectra. What wavelength you want to use with the laser depends on the application, and they range all the way from X-ray up to microwave ranges. Different materials will have different unique wavelength-dependent properties, so depending what laser you use, you're going to have different interactions with the materials. Part of what this leads to is needing specific optics for different types of lasers. So a mirror that reflects a UV laser will likely not be able to reflect an infrared laser as well. We also see from this interaction with materials being dependent on the wavelength that you're able to damage certain surfaces with some lasers, particularly shorter wavelengths, which can be focused to smaller spot sizes because of the optical diffraction limit, and have high energy photons can damage surfaces, or surfaces that are very absorbent to the thermal energy of a particular wavelength can be damaged by that wavelength laser. So here's an example of surface-induced or laser-induced surface damage to an optical coating on an element. So care needs to be taken that the correct optics are used with a laser system. A laser has an output power and energy, typically measured in watts or joules, and it's used to describe either the optical power output of a continuous wave laser or the average power output of a pulsed laser. Pulsed lasers are characterized by their pulse energy, which tells you how much energy per pulse are they emitting. And this is directly proportional to the average power and inversely proportional to the laser's repetition rate, so how often it sends out a pulse of energy. If we were to look at this graph here, this shows for lasers with different average output power, what pulse energy requires what repetition rate. So for example, for a 1 watt laser, if the pulse energy is 10 microjoules, then the repetition rate is 0.1 megahertz. So 10 microjoules times 0.1 megahertz gives us a 1 watt output. The pulse duration for a pulse laser is how long the pulse of energy lasts for. Typically, we measure this with the full width at half maximum. So if we look at a graph of the power output of the laser versus time, the energy that's being output by the laser goes up, reaches a peak energy, and comes back down. And the time between the energy output being above half that peak is the laser pulse duration. The repetition rate is how often these pulses come out. Usually it's specified in frequency. So 1 over the period or 1 over the time between the pulses is the repetition rate of the laser. Laser light is coherent, meaning that there's a fixed relationship between the electric field phase values at different times or locations. So what we mean by that is if we add up the different electric field phase values, essentially looking at the interference between different components of the wave, they have a fixed relationship. This is what allows for laser pulses. So for example, in this image here, we add 3 different frequencies, creating a localized pulse. This pulse will propagate through space and maintain its shape, assuming we maintain this coherence. This occurs because laser light is produced by stimulated emission, unlike most other types of light sources. Stimulated emission produces coherent light. Coherence does degrade throughout the propagation, and the coherence length of a laser defines the distance over which its temporal coherence is maintained to a certain quality. Laser light can be polarized. Polarization defines the orientation of the electric field of a light wave. That direction is always perpendicular to the direction of propagation. So for example, on the left here, we have the electric field oscillating up and down in the y direction, while the light propagates in the z direction. Over here on the right, we have the electric field oscillating in the x direction, while the light propagates in the z direction. Both of these are examples of linearly polarized light. There are some other options, such as elliptical or circular polarization. Often a laser is not fully polarized and will specify its degree of polarization with a ratio. For example, 100 to 1 would be saying that the electric field is 100 more times in the y direction than it is in the x direction. The beam diameter of a laser measures how wide the laser spot is. Typically, we characterize it in terms of the intensity drop-off from the peak intensity at the center of the laser spot. When the intensity has dropped to 13.5% of the peak value, that is what we define as the diameter. This 13.5 comes from 1 over e squared, which gives 13.5%. The power or energy density, typically measured in watts per area or joules per area, is related to the energy of the laser and the beam diameter. The larger the beam diameter, the smaller the power or energy density of the beam of a constant power will be. There is an optic for lasers called a beam expander, which is used to widen the diameter of the beam. Sometimes you may want to do this to keep from damaging optical components in your laser system. By widening the beam, there is less energy per area going through the optics, and there's less likely to be damage from heating. You do have to be somewhat careful that the widened beam does not clip any apertures, so you're not blocking out any light that you wanted to get through the system. The beam profile is the shape of the laser beam. There are many different ways laser beams can be shaped. Most typical is a Gaussian profile, but there are also such things as flat top profiles and components that allow you to shape the laser beam in various different ways. The divergence of a laser beam measures how the beam spreads from its smallest area. Ideally, we'd have a collimated beam that is just going in a cylinder. However, there's always some amount of divergence. The beam divergence is typically defined by the laser's half angle, and the divergence theta of a Gaussian beam is defined as the wavelength divided by pi times the beam waist. So the beam waist is at the narrowest point, how wide the laser beam is. then we can see that the beam expands and goes outward at this angle theta. The spot size of a focused laser beam describes the beam diameter at the focal point of a focusing lens system. When you're focusing the laser beam, there's a lot of reasons you may want to do this, and one of them is you can do things like micromachining. If you purposefully have a material that the laser will damage, you can mill small holes. You can also do things like photolithography, where you can make patterns in samples, and this is highly used in semiconductor processing industries. The working distance of a laser system is commonly defined as the physical distance from the final optical element in the system, typically a focusing lens, to the object or the surface the laser is focusing onto. Laser optical components need to be chosen with care for laser systems. Especially with higher powered lasers, it's especially important to consider the surface quality and coatings of the optics used in the beam path. Poor surface quality can lead to heating and damaging of the optical element, as well as scattering from the defect on the surface, damaging the coherence of the laser beam. Additionally, different optical elements in laser systems may work with one laser, but not another. Coatings are designed for use with specific laser wavelengths, so the optical component that works with one laser may not work with another. There are some common optical components that are used specifically for laser systems. For example, a beam splitter, pictured in the top here, is designed to take a laser beam and split it onto two separate paths. This is commonly used in interferometry, where a laser beam is split. One of the beams is sent through some optic, and then it's interfered with the other path. This allows you to tell something about the laser and how it passed through that optic. Beam expanders are designed to transform an input beam to a larger diameter output beam, and beam shapers are used to change the profile of a laser beam. So in this example on the bottom right here, a Gaussian beam comes in one side of the beam shaper, and the output is a flat top beam. The laser spot changes from Gaussian to flat top. This has been Different Considerations for Laser Systems. Thank you for watching.